Hi everyone, this is Neel Bhatt, and today I'm going to present to you a paper titled Reinforcement Learning Based End-to-End Parking for Automatic Parking System. And this is a paper that was published by researchers that are at the Tongji University in China and also at the SAIC Motor Company. And this paper was published in the MDPI Sensors Journal, and it was published in late 2019. Also, before I move on, this is part of the CS885 Reinforcement Learning course at the University of Waterloo. So just to give you some context and motivation, automated parking systems are a huge benefit for urban parking facilities, especially in areas where there is a high density of cars in especially urban settings. And this is of benefit because it increases parking safety as well as it enhances utilization rate of the parking facilities and offers convenience to drivers. Also, there is a standard from ISO which stipulates that parking inclination angle is to be confined within plus or minus 3 degrees. So this paper actually focuses on a DDPG based end-to-end automated parking algorithm, wherein the main assumption is that the driver manually drives and performs step 1. So the driver has to manually drive up to the space where the APS can do the reverse maneuver right here, and then the reverse maneuver is performed by completely autonomously by the APS. So in doing so, some of the related work it relates to mainly two main topics, which is path planning and path tracking. So path planning consists of trajectory functions that are predefined but have some parameters, for example B-splines or eta cube splines and so on. And these are trajectory functions that usually have some parameters that have to be geometrically and numerically optimized, and this are usually subject to vehicle constraints such as the various degree of freedoms for the wheels of the vehicles. And so this is what path planning is mainly about, but path tracking is often accomplished through feed-forward control using 2 degree of freedom vehicle dynamics model. So this actually comes after the path has been planned and the desire is to track that path. And in terms of control, there are mainly two methods that have been actively proposed. One is PID control and one is sliding mode control. So these are some of the related works, and in this specific problem the input is various camera images. So especially in this scenario, there are cameras that are mounted at the front, left, back and right. So this allows generation of a surround view image that can be stitched together. And the features of the parking spot at which the car is supposed to be parked include T and L shaped markings, and these are on the road. So in addition, an end-to-end scheme where these features are identified and represented internally is technically desired. However, in this paper, a separate vision-based detection module that deals with the detection of the T and L shaped marking as well as tracking for any missed detections is performed. So in that sense, this is not really a complete end-to-end solution, because it relies on another module that takes in the pixels and transforms it into a representation, which then can be used to detect the markings. So this is something that the algorithm expects from this module. So a little bit more about the problem background and the MDP formulation. As you can see on the video, the state usually consists of the features that correspond to the 4 coordinates at the corners of the parking spot, and the action refers to the continuous space of steering angle that's provided by the automated parking system. So this action is what we are trying to obtain, and the state transition function is unknown and is not modeled explicitly here. So this is a model free approach. In addition, the reward function over here is manually handcrafted. So essentially it's formulated as a contribution due to 3 main terms, wherein the first term is RCP. So RCP is essentially representing, intuitively at least, the deviation from the center of the parking spot. So we have this as the parking spot, and the center of the parking spot would be somewhere here, and essentially this first term in RCP, which is right here, this first term is essentially just intuitively quantifying the deviation from the center of the parking spot. And the second term is actually the error in the attitude of the car. So if the car has some inclination angle with respect to the face that's perpendicular to this 2D frame, that is essentially the attitude error that needs to be modeled and is modeled in the reward function. So essentially, if there is any inclination, then that results in a lower reward. And in addition, there is the line pressing term. So this term is essentially a constant negative reward that's given if any part of the car is crossing over the marking, or is currently on the lane marking. So essentially this is a reward intuitively given to penalize for any crossover or presence over the markings for the parking spot. And in addition, the lateral bias term is also a constant negative reward, and this is essentially the deviation of the rear axle of the car, the ego car, with the coordinates attached to the center of the rear axle, and the deviation in the y-axis is essentially taken into consideration here, so as to make sure that the vehicle aligns at least laterally in the center of this box. So a negative reward is given if there's any lateral bias. So now that we know about the MDP, the DDPG algorithm is derived actually from the 𝐷QN algorithm that we had talked about earlier in the lectures. So the DDPG is a model-free off-policy actor-critique algorithm. So it's essentially a modification on the vanilla actor-critique algorithm that we discussed in the lectures. And if you look at DQNs, actually, we have some sort of encoding features for the states, and once we have this states as an input, we can get as an output the estimate of the Q value for that specific state and for each of the possible actions. However, since we have our steering angle of the car that we want to learn, we essentially cannot deal with a table, a Q table of some sort, or this network with a discrete amount of actions, and instead we need a continuous action space. So essentially the DQN is not feasible for this continuous action space problem. So that is the reason why the authors have gone with the DDPG algorithm. And in here, the difference is we have added the actions as well for input to the critique algorithm. So essentially for the critique algorithm, which gives us the same Q value estimate, we have the inputs as the state and the action, and then it gives us a Q value estimate for that specific state and then that specific action. And the action is actually based on the mapping from the state space to the actual actions, and this is done through the actor network. And I will explain exactly how this critique and actor network are trained together in the next slides. So first, on to the critique network. We note that the action features are actually included as network inputs, as I explained before, and this is actually done so that we can in turn update the actor network in a meaningful fashion. But for now, the critique network is updated in the same way that we did with the DQN, wherein we have a target Q network, which is updated based on the hyperparameter tau, which is usually less than 1, and this essentially means that we're not updating the target network every step. So usually this is updated on the order of 1,000 steps or so, and this is just to ensure that the convergence of the critique and actor network does actually occur, because if we update the target network every step, then we could potentially have divergence due to the instability of this target network. So the temporal difference between the target and the Q network is used to perform the gradient updates, and this is the same as we did with DQN, where we updated this gradient based on minimization of the mean squared error loss function. And so this is how the critique network is trained. So for the actor, the training process is actually governed by the deterministic policy gradient theorem, as opposed to the stochastic policy gradient theorem that we talked about in lectures. So here, as expected, we do actually have the policy network, and in addition, we also have the Q network, which is the critique network in the gradient update. So the target network pi is actually still updated based on the hyperparameter tau. So we actually have a target network for the policy as well as the target network for the Q network. But the difference here is that when we want to update the actor, what we do is we utilize the Q function gradient as an error signal to update the actor parameters. So for example, we have some initial actor parameters for the policy network. And so when we start with this, we can have some state to action mapping based on these parameters, and then use these actions as an input for the critique network to give us a Q value estimate for that given state and action. And then if we take the gradient, so what we would do is we would take the gradient of the Q function with respect to the action, which is essentially taking here, because we're updating the actor network, what we're doing is we're taking the gradient of the parameters of the policy network with respect to the actions. Because what happens here is when we do that, we would have an estimate of the Q value for each change in the action with respect to the policy parameters. So we would essentially, in summary, tweak the policy parameters in a way that we obtain actions that maximize the Q value in the critique network. So in summary, what we do here is we take the gradient of the policy network parameters with respect to the actions, and then based on that we obtain a Q value estimate for that specific state and action to obtain the optimal Q estimate. And then based on this we will keep on updating the actor network. So as you can see, the DDPG algorithm training process for the actor does involve the critique network as well. So in terms of the network architecture, the proposed approach in this paper follows this training process both for the critique and the actor, except for the inputs we here have in the application the 4 corners of the parking spot. So since this is a 2D space, we have 2 coordinates for each corner, so we have total 8 inputs for this actor network, and they are mapped to the steering wheel angle, which is essentially just one node. And in this specific configuration, the authors have proposed 100 hidden layers, like the first hidden layers, and then 200 hidden layer nodes for the second hidden layer. So essentially there are 100 nodes for hidden layer 1 and then 200 nodes for hidden layer 2 in the actor. And in the critique, as I explained, we have a combination of both the actor and critique coming into play to take the gradients of the policy parameter with respect to the action that give the maximum Q value estimate. So in here, the number of nodes in hidden layer LS1 and LS2 correspond to the same as LA1 and LA2. So there will be 100 nodes in LS1 and 200 nodes in LS2. And also for LC1, which is essentially the number of nodes going from the steering wheel angle, the authors have proposed 200 hidden layers, 200 hidden layer nodes here. So this is essentially the network architecture, and now that we know about that, we can talk about the overall scheme. So essentially, as an input from the environment, we will observe the state, action, reward, and then the next state. So the action initially will be based on the policy parameters that we initialize, and then once we have this quadruple, this would be input to the actor critique training process, as I had explained, where we will be storing these quadruples into an experience pool, which is essentially an experience replay buffer, like we have talked in the lectures. And This is essentially done because in this specific reverse sequence we have dependency in the data, and so the experience buffer is implemented to remove that data correlation due to the inherent dependence of this observations in this reverse sequence. In any case, when we have this experience pool and this training scheme, the output would be the steering angle, which would be given to the controller for tracking, and this is essentially how the overall scheme is structured. So in terms of the experimental evaluation, the authors have tested this model, which has been trained on simulation and on real world sensor data, and they have tested it on initial approach angles of 60 degrees, 45 degrees and 30 degrees. So I will first start with the 60 degrees evaluation case. So in this case, they achieved an attitude inclination error of less than 1 degree absolute, and they compared this with the other path planning and tracking based approach, especially the PID and sliding mode control tracking approaches, and it can be seen that the inclination error is indeed higher for these other approaches, the PID and sliding mode control approaches. They are more than the specified or stipulated plus or minus 3 degree requirement from the ISO standard. So those approaches are hence not really practical. However, there is one anomaly here in terms of the DDPG RL based agent, and that is that the path that's taken does not actually follow the reference path very well, and this is because the reference path is inherently not present in the reinforcement learning model. It's just present in the path planning based models because they're structured to have that path planning done, whereas the reinforcement learning does that implicitly. And this could be problematic in cases where we have narrow parking spaces adjacent to each other, and for example, if we had some cars that are parked very close or even on the parking space limits, then it could be possible that the vehicle, while making the maneuver, could intrude onto the other vehicle parking spaces and cause potential collision. So this is something that's the downside of this approach, and I will talk about this later on as well. So moving on to the cases for 45 degrees and 30 degrees inclination angle, the attitude error actually remains less than 1 degree for both of these cases, and as you can see, the tracking performance is better for these lower inclination angles, but the problem does still remain, and the tracking error is actually indeed more than the path planning based methods. So based on these experimental results, we can conclude that there was significant improvement in the inclination error. However, the tracking issues still remain with this method, and it cannot be customized for unseen scenarios, especially for the scenario where that I mentioned, where it is possible that the vehicle can intrude into the space of the neighboring parked vehicles, and also for cases where the initial inclination angle is 90 degrees or larger than 60 degrees in general. As we saw, the tracking performance can degrade even further. So this is the main downside of this method. And in addition, we need to ask this interesting question, which is the claim of the approach being end-to-end really valid? Because the proposed approach actually takes in inputs directly from the module that's responsible for detecting this features about the parking spot, especially the corners. And in this paper, at least, there's this separate module that does this detection and also tracking in case of loss of any frames. So since this approach relies on a separate module to take the input pixels from the image and transfer it to the detected parking space markers, I wouldn't really call this an end-to-end approach. In fact, DDPG's original proposed authors claim that this approach is suitable for end-to-end based learning, especially taking inputs as image pixels and transferring it directly to sensory outputs like steering angle. So I wouldn't really claim this is an end-to-end based approach. And finally, for some future directions, since the reward function here is essentially handcrafted, it is expected that the reward that would be obtained by this algorithm is not optimal. So instead, if the inverse reinforcement learning algorithm is pursued, both the reward function can be estimated inherently and can be optimal, and in addition, the problem of the continuous action space can also be dealt with, because in reinforcement learning we can still go ahead and do the calculations for the continuous action space because of the scheme proposed in inverse reinforcement learning. So I would suggest, and actually the authors suggest too, that the inverse reinforcement learning framework be tried, or at least be explored in the future to overcome the handcrafting of the reward function at the very least. So this concludes this talk. Thank you for listening.